Well, thanks for coming again. I mean, some of you missed my last presentation in the Bits and Pretzels, so I'm very excited to just talk again. Alright, deep learning. It's not a very obvious term of what we are talking about, so I just wanted to be very clear that deep learning has nothing to do with self-consciousness, self-awareness, meditation, or whatsoever, nor does it have anything to do with Albert Einstein. But this talk is going to be a lot about computers and how smart computers can be, and it's something that's beyond our imagination at the moment. So I was around 10 when I got my first video game, one of those, you put your cassettes, not the DVD or CD, but those that came with 100 games in it, black and white. And I was super excited. And of the many games that you could play on it, one was Super Mario, of course, but it turns out I was really bad at it at the beginning. But still, it was the best thing I could do at the time. Play. It was so nice to play a video game, finally, after asking my dad for a long time. So I just kept playing and learning how to just, do it better. And then after playing for a very long time, from being very bad, I got better. And I just did it myself. My parents actually didn't teach me to play. Actually, my dad is probably worse than me, still. So what if I tell you that it's just not us humans that could do such things, learn on ourselves, but also computers. And indeed, this is a clip of a computer playing the game, not me. A computer that learned by itself how to play the game. I'll tell you in details how it did the whole process, but now for the timing. I just said learning, a computer learns. So you might be wondering, how does it learn? Because most of us think that humans are the species that can do some things that other things can't, and computers are not even living things. And it becomes even harder to understand that computers can learn, because we know computers from a very day-to-day traditional way, where to solve a problem, you write a piece of code, or some cases you use softwares like Excel or PowerPoint to do your task. And coming back to code, not PowerPoint, a typical code looks something like this, where you have loops and numbers and some arithmetic. And so you can say that a computer can be only as smart as the programmer who writes the piece of code. A code basically where you just have only few tools to describe your way to solving the problem. But as the problem becomes more complex, it becomes harder to express your solution in terms of code that we saw before, especially in terms of loops and conditions and simple arithmetic. And especially in cases such as this, where the problem is to describe the scene in the picture. You just have an image and you have to describe what you see in there. A human can very easily say that, well, I see a bed which is on top of a carpet, which is lying on the floor, and around it is lots of furniture, like a dressing table and a shelf and some lamps and a window behind it. But for a computer to do it, that's very difficult, and to even a programmer to express that solution and how you came to that conclusion in terms of code is very difficult. So this is where machine learning comes in. Simply to give you an idea of what machine learning is and how machine learning is different from typical programming that we do. I'll give you an example here. Let's say you want to write a piece of code that could differentiate between apples and oranges. You have some data, and you figure out that apples normally weigh between 100 to 150 grams, and oranges between 150 to 200 grams. And you also know that apples are normally smooth, oranges are rough. Now let's say you have a fruit that weighs 110 grams and is smooth. Your code would most probably say that it's an apple. And vice versa, if you have a fruit that is rough and weighs around 170, 180 grams, your code would simply take that and compare it to the data you have and say that it's an orange. But what if your fruit is smooth but only 90 grams? In this case, it's most likely an apple, but your code would fail. It's because your code was simply comparing your fruit with the data you had. And your example here was just outside the data you provided. Obviously now you can think of collecting more and more data so that you can have every case of comparison for every sort of fruit that you can find. But this is simply just not possible. So a smarter way to go about it is to have a piece of code that does not simply compare your fruit with the data you have, but learn some sort of abstract information from the data you provided. Or even better, it learns from the past guesses it made, from the correct and the wrong guesses it made. And this is the process where it learns on its own what an apple or an orange is. And this is what is, in its sense, machine learning. Machine learning to describe in steps consists of three basic processes. The first is obviously to get a set of data that you want to train your software on, or your code on, your machine learning code on. Once you have the set of data, the second step is to extract some sort of information, like I said before, some sort of high-level information from the data so that you can learn what you're trying to say. For example, in this case, we are trying to recognize faces of different people, and we want to learn some way to describe those faces so you can finally learn whose face which one is. Typically, this process of extracting features go on in a hierarchical process, which is in a stepwise, from very low-level features such as the contours, by which I mean something like the edges or the vertices or the points, the different points or the lines around the faces. And then the second step is to take those lines and the points and put them together to form those parts of your faces, like the eyes or the nose or the lips or the ears. And once you have them, obviously the natural way to go about it is put them all together to get the face itself. That is the high-level abstraction. Let's say you have succeeded to do that process. Once you get there, the next step is to learn from those abstraction the names of the faces. This is very simple. If you describe it this way, it sounds very simple and very clear what to do in any machine learning case, any problem you have to solve. But the biggest trouble is here. How do you accomplish that? Because the only way you can do that is write code, and I've already told you it's very difficult to express such things from a human understanding to mathematical point of view. This is where deep learning comes in. That extraction of features people have been doing that for a long time now. Machine learning has been there for a very long time, and people has been using it, and very good results have come out of it. But most of the time, actually all the time, scientists have been extracting those features very manually, by very selectively studying the problem, trying to figure out how you can write that code to extract those features, and then finally have a machine learning tool that can solve a problem very specifically. And that's all. It cannot be applied anywhere else. Deep learning is something different. But first I'm going to give you an idea. what deep learning or neural networks are. Simply to understand, it's a layer of connected nodes. It's like the neural network we have in our head, connection of neurons. Each circular dot over there is a representation of a neuron, which is an artificial neuron. And what the function of this neuron is simply to take information, let's say that one, it takes information from other nodes behind it and does some sort of mathematical computation on top of it and gives you an output. Let's say you get numbers here, it simply adds up the numbers and gives you the sum of the numbers on the output. And then it goes on and on from the first layer, which is the input layer where you give the data, to the last layer, which is the output layer, which predicts, for example, in the case of recognizing faces, you would predict the name of the person whose picture you gave to the input layer. Now, for the working of a neural network, obviously you start with giving the data, and then the functions of those many layers in between are to extract those features that I talked about, but this time it does it automatically. You do not have to tell anything about how to do it. And the best thing is, it turns out that this network does the same process. The first few layers of the network tries to extract the very low-level features, the edges and the points, the dots that I talked about. The layers in between tries to combine those information from those layers and then form it into the parts of the faces, like the eyes and the nose. And the layers at the end combines those information and then gets the high-level abstraction of the face. This is exactly what humans have been doing for years and years now, but the network simply does it automatically. And this is good because now you can completely avoid wasting or spending a lot of time trying to come up with the math to how to do this. That was a very basic understanding of basic representation of neural network. Obviously, there are different types of neural networks that you apply to very different types of tasks. For example, when you do something with pictures, you take a network that I showed, which is called a convolution neural network. But for example, you're dealing with speech or audio, for example, Siri on your phone that recognizes your voice and whatever you tell it. You use a different type of network, which is called a recurrent neural network, but it's very similar, just the structure is a bit different. And also there are some other kind of problems that scientists have been trying to tackle recently, and those are generation of pictures by itself. For example, you tell the network, give me a picture that looks as real as could be of a cat, and it tries to give you a picture. It's like a picture from your phone or your camera, not like a picture you draw. And it tries to generate that. And those kind of networks that people use for solving those kind of problems are called GANs, or generative adversarial models. Alright, so now we have a basic understanding of what deep learning is and how people apply it. So I can tell you now how the computer actually learned to play this game. So on the left side is a frame-by-frame playback of the game after the computer learned to play it for several hours. And on the right side is a sort of representation of the different things that the computer is looking at every time step. To break it down, how did the programmer write the code for this? What he did was basically take a deep network and give it the picture, the frames of the game as an input, and the output of the network is basically the controls to the player, which is moving left, right, up or down, one step at a time. And then he said, all right, here's the deal. If you die before going to the end of the level, you get a -1. And if you get to the end of the level, you get a +1. And then it says, now try to play the game. And then the computer tries, step after step, one after another, it tries to go as fast as it can But obviously at the very beginning it can't go any further because it hasn't learned anything about it. But as it keeps on playing the game, it learns every time, all right, if I do that move, it led me to dying, so I'm not going to do that again. For example, if I step on a turtle, I die. So I'm not going to do it again. So I'm going to avoid it by trying to jump over it, which is something that he learns again. So he does that over and over again, then he gets sort of representation of the game here and what he should do and what he shouldn't for everything that happens in front of him. And at some point he has a very good understanding of how to play the game and tries to reach the goal that he was told as fast and as efficiently as he could. This could be very well seen in the game itself. If you pay attention, he was never told that collecting coins, for example, those things are coins, is a good thing. He was never told about it. So he doesn't really care about collecting. Sometimes, well, that was very coincidental because he had to jump over the turtle. But otherwise, he doesn't try to collect coins because he was never told that collecting coins is a good thing. Obviously, you can change that when you train the network, but all he was said was to try to reach the end. So he tries to go there as fast as he could, jumping around, and you can see it's not really how a human would play the game, because I would try to collect as many coins as I could. And on the right side here, this graph is basically a representation of how he's learning the rewards that he would get from each step, that time step, based on the action that you'd be taking. For different actions, what kind of rewards you'd be getting and what his long-term reward would be. And he tries to optimize that long-term reward because the goal is to get as many points as you can, the +1 and -1 points. And on the right, on here is simply the frames that were fed to the network and were corrected to a grayscale image so that the processing becomes easier. And then he just takes those pixels and the network goes through those pixels trying to understand what's happening. The programmer never said that a coin looks like this or that that's actually you in the game, that's something else. It's never told anything. The network tries to learn all of that from there, and the white box over here is basically the part where the network is focusing at the moment to try to play the game. And it turns out it's actually focusing on itself most of the time. Alright, so that game and the process that was used for the learning has a specific name. It's called reinforcement learning. Reinforcement learning is a process where you give goals and then you give awards and punishments. There are two other types of learning processes. The one is supervised learning, where you have labeled data. For example, you're trying to learn different categories of things. For example, you're trying to detect furnitures and you have different kind of furnitures, chairs, tables, and you label them. This is how a table looks like, that's how a chair looks like. Then it's called a supervised learning technique. The last learning method is an unsupervised learning technique, and it's the most difficult of the three because here you do not really have labels. When you give the data to your network, all you do is, here you go, this is data, I have no more information on top of that. And you ask the network to try to classify it or cluster it into categories that it thinks is the most appropriate. For example, here, it's probably a very ideal representation of how the end result of the classification would look like, where the triangles are all together, circles together, and the crosses are together. But that is something that you try to achieve using the network. We have seen an example of the game played by a computer, and it looks quite good. And also there are many examples on how people are using deep learning. For example, driving to facial recognition, to Siri or Google or Alexa, or so many different tools using deep learning. But we still need to ask the question, how good is it really? Is it just okay when you apply it, but not as good as it could be, hypothetically speaking? Or is it actually very good? And there are very good benchmarks on this on these comparisons of deep learning with other methods and even humans. And this is one of them. This is a benchmark on image classification. There are around, the data set is called ImageNet, which is on the internet, and there are around 1,000 different categories of objects like cars, trees, buildings, etc., and around over 1 million pictures labeled by students of universities. And people have tried different networks on it and different learning methods, and there's a competition that goes on every year on this. And this graph shows a very interesting thing about deep learning. Here, anything before that, which is around 2010, 11, people weren't using deep learning. People are using traditional machine learning technique where scientists sat down together, was like, oh right, we need to write a piece of code that can recognize pictures. And so this is timeline obviously, and on the y-axis is the error rate, which is basically how many misclassifications you have done. So you can see before using deep learning, the percentage of error was so up high. And suddenly deep learning came in and people started using those networks, which was also very easy to apply because you do not have to sit down and try to solve how to do everything by hand because the learning process is very automatic. But deep learning itself is actually very good because it already after 2 or 3 years, I think, it goes down to almost around human, this is a benchmark human result where many test subjects were tried on the dataset and they had to classify pictures, and it came out to be around 5%. Obviously, individuals differ slightly from each other. But currently, we are actually we are below that human performance, so we are actually better. And this shows that deep learning indeed is actually very powerful. It's just not good that you can apply, but it's actually very powerful. It's very powerful, way more powerful than other machine learning tools. That was performance. The other question that you need to ask is about how well do these systems scale? Because when you think about applying deep learning to actual practical problems, things become very complicated. One of those variables that this graph tries to analyze is the amount of data. Obviously, we have more and more data every day, so getting more data is not a big problem. So let's see how the performance goes up, or if it stays slow, as we put more amount of data. The green line over here is the non-deep learning machine learning techniques, the machine learning techniques that came before deep learning. And it turns out at some point, no matter how much data you give in, it doesn't go up. It just stays there. And that's because those systems are very specifically engineered for the problem by humans. They wrote the code, the math behind it. So at some point it just saturates and it cannot adapt to the overwhelming dimension of the data. But on the other hand, deep learning, which learns everything automatically, starting from the low layers to the high layers, it just keeps going up and up with the amount of data you have. Obviously, it's not that easy as it looks like here. You always have to optimize things. As the data becomes bigger, you have to check if you have a big enough network, for example, to take those data in. But it's possible. You have to, if you can expand the network, the performance would go up. And this is something that people haven't achieved before in the area of machine learning. So if all of that was very overwhelming, I'm just going to give you 3 takeaway points why we would use deep learning in the future and the potential that it has. The first one is obviously because it automatically extracts all the information from the data that it needs to solve the task. And it saves a lot of time. Second, those networks that I've shown, for example, the network that was used to play the game, could be used to play another game or even solve something that is quite similar to the game. This is different to other machine learning tools where once you have a machine learning tool to solve a problem, for example, classifying pictures, you cannot use that to solve another problem. You just not get good results because it's very optimized. It's for that specific problem. And this is good because it takes time to create a tool, and once you create the tool, you want to use it to solve different kind of problems. And the last thing is deep learning scales very easily to data and to using bigger networks. And if you have more GPUs on top of that, that is the more hardware to do the computation on, you would get better results. This brings me to the end of my presentation, just the last part where I'm going to talk about there are two sides to this picture. The people who talk about, scientists who talk about deep learning is just a hype. It's here, but it's going to disappear after 5-10 years. People are just crazy about it, but in 10 years, no one's going to think about it. But there are the other half who thinks that they do agree that there's not lots of concrete science and math behind it, but it's going to be a revolution. People are going to use deep learning, people are going to study it, and it's going to change the way that computers are used in our day-to-day life. And we can already see a picture if we hold a neutral opinion on this. The sort of applications that deep learning has been into starts from finance. For example, people are writing code to predict stock prices by just going through the news and trying to guess which stocks would go up or down today because of the news. I'll show a few of those, or one or two of those demos so that you can just feel like get an idea of how cool deep learning is actually. But different stream is arts or entertainment, where, for example, there's I'm going to show that later on. A computer create a script for a movie. Obviously, it was a 15 minutes movie, but the script was generated by a deep learning network. It was given a lot of different other movie scripts, and then it gave out a new script for a new movie. There are tools already that could transform simple strokes on a canvas into a painting that looks like a painting by someone as great as Van Gogh. Or a very interesting thing that I came to learn recently is how Netflix treats you differently from the other people. Every movie has a thumbnail on the Netflix screen, and that thumbnail shows the picture of the actor or someone on it. And Netflix collects data on you and tries to predict what kind of person you are, what kind of genre you like watching, comedy, romance, action, and based on that, for the same movie, you would put a different character on the thumbnail, depending on if you like someone funny. For example, he would put, for example, if there's Adam Sandler in the movie, Netflix would put his picture on it rather than someone more serious. But if you like a romantic flick, for example, you would see a picture of a couple on it, rather than something that could look more like an action movie or a comedy. And to some point, you might actually talk that this might be crossing the line, but that's a different discussion that we can have it on a different day. Another area that I do not have to mention is autonomous driving, where people are trying to use deep learning and replace other machine learning tools, specifically because of the dimensionality of the data that comes in from the car sensors, different various number of sensors, and then the complexity of the model that you have to build of a real world around you. Something that we have seen already, that deep learning is good at adapting to dimension, complexity of data. Something very interesting to us perhaps is there's a startup which tried to use deep learning to transform mock-ups that a designer would create of the different layouts of the app into code directly, because if you think about it, writing code for layouts, it's a very mechanical job. It doesn't need lots of creativity. You know how to write a view, how to write a controller. So if it's well defined, you can transform those designs into layouts, and there's a link to that on my slide. And that startup came up with this tool that could do that, but up to an accuracy of, I think, around 80% or so. So it's not there yet, but the kind of application that deep learning has been the kind of problems that deep learning has been applied to is just very interesting. Media, another very controversial application. Fake news, for example. There are tools that you not believe that could take a video of a person and make it say whatever you want to based on an audio clip that you give. For example, a video of Obama talking whatever that you want to tell him to tell you on news. And if you see that video of Obama telling you that tomorrow this is going to happen, are you going to really doubt that? No, you're not, because you see him, the person, talking. And this is going to be very difficult once this actually comes out as in the fake news mainstream. Recently I watched a movie. It's about the movie Morgan. It's a thriller movie on artificial intelligence. Couldn't be better, as an example. And the producer of the movie, they approached IBM, and they asked if Watson, their intelligent machine learning system, if he could take the movie and create a trailer for the movie. Now, before I show you the video, I just want to talk just a few words about how it was accomplished. To create a trailer, it's a very, very tricky job, because you cannot give away anything that spoils the movie, but you have to make it interesting enough for people to come to watch the movie. It's the biggest advertising media for movies. Specifically, people watch trailers before going watching the movie. So IBM took the movie and then segmented it into different parts of sadness, happiness, by analyzing the pictures and the audio in it, and put it into different clusters. And once it did that, it took different trailers of different movies and tried to learn how a trailer looks like. And then once it had the two information, it went back to those parts of the movie, the parts it made out of this movie, and then took the segments that it thought is how a trailer is made.
Skip, don't go in there, okay?
Don't what?
Don't you go down there, Skip!
Don't be afraid, Amy. I have to go say goodbye to Mother.
Now, the trailer doesn't really tell you what's going to happen in the movie, but it's a very it builds up the suspense like it does in any kind of trailer for a thriller movie. But obviously, you have to know that, which I'm not sure about, but I think that the audio was done afterwards. Someone actually created the audio for it, because the audio doesn't come from the movie and it only takes parts of the movie. So it doesn't talk much about how the background music was created, which also adds to the suspense of the movie. But obviously nevertheless, from the clips, you can see that it doesn't tell you anything about what's going to happen, but builds on top of each other, which is quite amazing. And it made me watch the movie, so I guess it worked. All right, well, that was basically the end of my talk. Thank you so much for having all your patience and listening to me. I think I took a lot of time, actually, but if you have any questions, I'll be very happy to answer. And if you want to discuss about things, that as well. Thank you so much.